Hi everybody. In this video we are going to see what is a graph and what are the different ways of representing the graph and what are the graph traversals we are having, that is breadth first search and depth first search. So we can discuss with a suitable example. First we are going to define what is a graph. So as per data structures we can define a graph is a non-linear data structure which can be defined simply a group of vertices and edges. So mathematically we can represent a graph G equivalent to the pairs of V comma E. So here the V represent the set of vertices and E represent the edges set. So coming to the applications of the graph where we can use. So we have so many applications and we can apply graphs for the computer networks, social media, routing algorithms, GPS, web searching, project scheduling, deadlock detection, circuit design, and if you want to do some shortest path algorithms like finding the minimum spanning trees, minimum shortest path, and all these are internally we are going to use the graph data structure. Now we will see how exactly we can represent the graph. So there are two ways. The first one is we can represent the adjacent matrix. So here in this example I am having 5 vertices A, B, C, D, E. That means when you want to represent this graph as a matrix, we need to define 5 by 5 matrix. So 5 by 5 matrix A, B, C, D, E, A, B, C, D, E. And wherever the edge is present, from A to B, the edge is present. So from A to B, the edge is present. So you can represent with 1. And wherever there is no edge, we are going to keep 0. So by filling all these details, finally you will get the adjacent matrix for the given graph. So for given graph, we can identify wherever the edges are present, we are going to represent with 1, and wherever the edges are not present, we are going to maintain with 0. So this is one way to represent the adjacent matrix. And we can also use, there are two types of graphs I can use. So directed graph, undirected graph. So this is an example of undirected graph. Undirected graph means there is no direction between the flow of the edge. So here the edge is present from A to B as well as B to A. So B to A is also present. B to A is also present. Coming to the root, for example, if the edge is present from A to B and the direction is represent like this. So automatically I need to consider the edge only from A to B and there is no edge from B to A. So for B to A I have to keep 0. So according to the direction of the edge we need to represent these values for directed graph. I hope it is understood. The next way of representation of the graph is we can use the adjacent list. So here it is undirected graph where I am having 5 vertices A, B, C, D, E, and you can represent A, B, C, D, E, and you can identify all the adjacents from A. So from A I am having the adjacent B, I am having adjacent C, I am having E. So from A I have the adjacent B, then C, then E. So first you can maintain all the vertices as headers and each header can be connected with the number of nodes. So like your linked list. So each node will have represent the adjacent of this A. Similarly from B, what are the adjacents I am having? A, C, D. So from B I am having adjacents A, C, D. Similarly from C I am having A, B, E. From C I am having A, B, E. Next, what are the adjacents I am having from D? From D I am having B, E. So 2 adjacents B, E. From A I'm having adjacent A, C, D. A, C, D. So this is how I can represent with the help of adjacent list. Coming to the traversals. So there are two traversals we are having, breadth first search and depth first search. So first we will see what is BFS traversal. So the BFS traversal, we are going to use internally the data structure queue to keep all the visited vertices list I'm using, and I'm keeping the data into the queue data structures. I can explain with an example. And coming to the applications where we can use this BFS to identify some shortest path algorithms, to identify the social networking connections, web crawling, and broadcasting in the networks, finding the connected components of the graph. For all these things, we are going to use BFS algorithm. So I can explain with an example. So this is the given graph. So I want to identify what is the breadth first search traversal of this graph. So what exactly the meaning of traversal? Traversal means I need to visit all the vertices in the given graph, right? So here I am starting my BFS traversal from the source node A. So initially I can keep all the vertices A, B, C, D, E, F, G, H as visited 0, and there is no data in the queue. It is empty. I am starting from A. So now I visited vertex A. A is visited. So you can mark this as visited. So the list visited represent 0 or 1. 0 means not visited, 1 means it is visited. So the vertex A is visited and A is inserted into the queue. Now you can pop out, you can remove the element from the queue and search for all the adjacents from that vertex. So now you can remove A from the queue and you can search what are the adjacents present for A. So for A, I am having two adjacents B, C, B, C. So now you can make BC as visited and send this BC to the queue. And A you can put into the BFS output. You can add for the BFS output. A it is there. And in queue I am having B and C. And coming to the visited list, already I visited A, B, C. Now you can remove B from the queue. So you know the operations of the queue. How exactly the queue will be working? First in, first out. So first I inserted B. So remove B from the queue and you can search what are the adjacents present for the B. So for B there are two adjacents D and E. So next you can visit D and E. So now you visited D, E. So make these two as visited and include this DE to the queue, and that B will be sent for the output. So your output is AB. And in the queue I am having the next vertices which I am supposed to explore the adjacents for C, D, E. And all these vertices already visited A, B, C, D, E. A, B, C, D, E. Now you can take the next element from the queue. So what is the next element I am having in the queue? That is C. So take the C, identify the non-visited adjacents. So non-visited adjacents, what I am having F and G. So now you can visit FG and make these two as visited and add this FG to the tree, and C is sent for the output. And next you can take E from the queue, identify its adjacent H. H is visited, H is sent for the queue, and D is send for the output. So now you can remove one by one element from the queue and check any unvisited adjacents present for each node. If it is there, you can include for the traversal. Otherwise, you can simply discard and send for the output. So when you are checking for the next three elements, for F, there is no new unvisited. So you can directly send F here. Next, you can G. From G, there is no unvisited vertex. You can send for the uh, output. Then you can remove H. From H, there is no new adjacents. So you can send for here. So finally, the queue becomes empty and all vertices are visited. And this is the output I will get. A, B, C, D, E, F, G, H. So that means I am visiting A, then B, then C, then D, E, F, G, and then H. It is level by level traversing. So we can also call this BFS traversal is level by level. So first level I visited A, next level I visited BC, the next level D, E, F, G I visited, then finally the H I visited. Coming to the algorithm steps for BFS. So choose any one node randomly to start your traversing. So in this example, I started from vertex A. Next, visit its adjacent unvisited node. So mark it as visited in the Boolean array and display it. The next step is insert the visited node into the queue. So whatever the nodes you are visiting, those visited vertices you are keeping into the queue. If there is no adjacent node, remove the first node from the queue and repeat the above steps until queue is empty. That is what exactly we did. We started our traversal from one node and we are keeping all the visited vertices status in the visited array, and whatever the vertex I am visiting that can be keep into the queue, and we can remove one by one vertex from the queue, and we are adding all the remaining adjacents from that one, and we are repeating this process until all the vertices what I am keeping into the queue becomes empty. So these are the algorithm steps we can follow for the BFS, and this is how exactly we can identify the BFS for the given graph. Now we will see depth first search algorithm. So how exactly we can travel by using DFS algorithm. For this DFS algorithm, we are going to use stack data structure. We are going to use stack data structure, and most of the problems which is depending on the backtracking procedure. So we are going to use this DFS algorithm, and there are so many applications we can use. So we can apply this DFS for different Graming trace out, different possibility of solutions for the given problem and all. And this is the example. So we can start our traversal from one node, and every time I'm going to include only one adjacent at a time. So in DFS, first I can start my tour from A. Then I am choosing one vertex from A. So after visiting A, I am visiting B. From B, I am visiting D. From D, I am visiting H. From H, I am visiting E. So A, B, D, H, E. So from E, there is no other choice to reach the remaining vertices C, F, G. So then what we need to do? I am going to go back to one step ahead. So from E, what is the previous step? H. From there, is there any possibility I am checking? Yes. From H, I have the possibility to visit F. Yes. From H, F I can visit. After visiting F, I can visit C, then G. C and then G. So here I can also visit either H, G, C, F. Any order I can visit, because every time I can include only one adjacent at a time. So generally, whenever you are identifying the BFS algorithm, the unique output everybody will get. But when you are exploring this DFS algorithm, multiple outputs we will get, because at a time I can select only one adjacent at a time. So that is the difference between BFS algorithm and DFS algorithm. And this is how exactly the data will be keep in the stack. So first I visited A will be keep here. Then I can visited B, push that B into the stack. Next from B I am visiting D. So D is pushing into the stack. After D I am visiting H. So insert H here. So after visiting H I am visiting F. F will be keep here. So after F I can push C. So whatever the node I am visiting, the same order you can push into the stack. So after visiting all these A, B, D, H, F, C, G, so graph is not fully travels because some elements not at all visited, and there is no scope to visit from G. Then what we need to do, you can pop out this and check for the possibility from C. If from C there is no other possibility, pop out next element. So pop C, and what is the next element I am having? F. From F I am checking. If it is not there, pop out F, you will get H. From H you can check. Yes, from H I can identify new adjacent E and you can visit it. So from there all the vertices already visited and you can pop out all the elements from the stack. And when stack becomes empty means all vertices are visited and explored. So this is how exactly the DFS algorithm can work. And these are the applications, general applications for DFS algorithm is for topological sorting we can use, for path finding, to solve the different puzzles and mazes games, to detect the cycles in the graphs, and we can also finding the connected bi-connected components also we can identify with the DFS algorithm. Coming to the time complexity, both DFS and BFS algorithms will take the time complexity of order of V plus E, where V represent the number of vertices in the given graph and E represent number of edges. So your time complexity for DFS and BFS algorithms is order of V plus E. Coming to the algorithmic steps for DFS, so you can start from the source vertex and mark the source vertex as visited. Now you can visit one unvisited adjacent vertex. So you start your tour from the source, and every time you are going to visit only one unvisited adjacent vertex, and you are going to repeat until no unvisited adjacent vertex remains. And finally, backtrack to the previous vertex if you are not able to find the complete solution from any one particular point. So every time you can backtrack one step ahead, then you can identify, go back to the one step and you can identify is there any solution for the problem. So these are the steps we can follow for the depth first search algorithm. So this is about DFS algorithm of your graph. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.